Okay, so we're going to talk about graphing a function, and you can see it's like really complicated. 8 steps to graph a polynomial or rational function. A rational function is a ratio or a fraction of polynomials. Polynomial in the top, polynomial in the bottom. What is a polynomial? A polynomial is a sum of ax to the n's. Polynomial is a sum. A polynomial in x is a sum of ax to the n's. Okay, so these 8 things, it looks like a terrible problem because it makes you fear that you're going to have to memorize all that, but you will never have to memorize all these 8 steps to graphing a rational function. Any one of them is a good problem in its own right. And you might be asked to do just like one of these things, or maybe 2 of these things. Evaluate a function at 0 to find the y-intercept. So substitute 0, and the output is the y-intercept. Find the numerator, factor the numerator and denominator. So factoring kind of is important in these problems. For factors in the numerator not common to the denominator, so you got factors that you can't cancel out, determine where each factor of the numerator is 0 to find the x-intercepts. So for simplified form, find the zeros of the numerator. For simplified form, find zeros of the numerator. Find the multiplicities of the x-intercepts to determine the behavior of the graph at those points. Does it go straight through? Does it bounce off the x-axis? Does it wiggle? For factors in the denominator, note the multiplicities of the zeros to determine the local behavior. For those factors not common to the numerator, so again, simplified form, find the vertical asymptotes by setting those factors equal to 0 and then solve. What is an asymptote? A line that a curve approaches. So for simplified form, find zeros of the denominator. For factors in the denominator common to factors in the numerator, find the removable discontinuities by setting those factors equal to 0 and solve. So what this means is you're finding holes in the graph. Find holes in the graph. Compare the degrees of the numerator and the denominator to determine the horizontal or slant asymptotes and sketch the graph. Now on that point number 7, horizontal or slant asymptote. I want to focus just on the horizontal asymptote. A horizontal line that a curve approaches. Okay. And that is a really, really easy thing to do. You can do it mentally. You absolutely can just do that mentally. So let's see, why that's so easy. Well, you look at the degree of the top and the degree of the bottom. What is the degree? The highest power on x. So do that for the top and for the bottom. If the highest power on x, say third degree, is the same as the highest power of x on the bottom, then there is a horizontal asymptote, and it's y equals the ratio of the lead coefficients. Y equals the ratio or fraction of the lead coefficients. So it's just a number, but it's probably not going to be 0. Okay? You're going to have 0 when your degree of the top is less than the degree of the bottom. So that can be done mentally, right? Then it's automatically the answer to the what is the horizontal asymptote problem. The answer is automatically y equals 0. That's the equation of the horizontal asymptote. That actually is the x-axis. Finally, when the degree of the numerator of a rational function is greater than the degree of the denominator, you might have, say, third degree in the top, second degree in the bottom. There just is no horizontal asymptote. So you can see that and do that mentally. So the entire horizontal asymptote problem can be done completely mentally. Now, if there's not a horizontal asymptote, then there might be a slant asymptote, which would be not really an easy problem. That's when you have to do division. Fortunately, most of the time, you can do synthetic division, which is a lot easier than any long division of polynomials. Okay, so here's an example. Find the horizontal asymptote. It's the line y equals 6/9, right? 6 is the leading coefficient in the top. 9 is the leading coefficient in the bottom. 6 divided by 9, or 2/3, the line y equals 2/3 is the answer. The answer is not just the number 2/3, okay? And it will not count as mastery. It's not enough evidence of mastery just to say the number 2/3, because if you just do that, I don't know that you know that a horizontal asymptote is a line. And a line is given by an equation. So you have to say it's the line y equals 2/3. Okay, so let's graph a rational function. Here's a rational function. It's a ratio of two polynomials. Actually, that's not the one I wanted to do. This is the one I wanted to do. Okay. So now let's go through these 8 things and see how they work. Evaluate the function at 0 to find the y-intercept. Okay. Well, that's easy to do. Most of these are just easy things to do. It's just when you put them all together, they seem overwhelming. But evaluate the function at 0. Okay, f of 0, that's, it's all this stuff. The square of 0 plus 1 times the square of, or not the square, but just quantity 0 minus 3 over all over product of the square of 0 plus 3, just plugging in 0, 0 minus 2, and what is that? That's 1 times a negative 3, 9, and a negative 2. So negative 3 over negative 18. One-sixth. Okay, so the y-intercept is the point 0, 1/6. Okay, so we have a point that we can put on our graph. Zero 1/6 is the y-intercept, so that's important. Zero 1/6. Number 2, factor the numerator and denominator. Well, they are already factored. 3, well, factors in the numerator not common to the denominator. Determine where each factor of the numerator is 0 to find the x-intercepts. And you can see that there is no factor common to the numerator and denominator. Okay, you can't cancel anything here. Right? It's not like you could cancel the x's out from inside the parentheses. That doesn't work. Okay, so we're going to find the x-intercepts by finding the zeros of the numerator. What are the values of the numerator? What are the values of x that make the numerator 0? Okay, so we're going to set the numerator. Let's see, this is 3. We're going to set the numerator equal to 0. Okay, now hopefully it's clear that x equals -1 or x equals 3. Okay, so x-intercepts are -1, 0, and the other x-intercept is 0.30. I hope that's clear that these are the solutions to this equation, right? Because, for example, if you put if you put 3 right there, then you have 3 minus 3, which is 0. 0 times anything is 0, and you have the truth. Well, we now have 2 more points that we can plot. -1, 0, 3, 0. 1, 2, 3. Find the multiplicities of the x-intercepts to determine the behavior of the graph at those points. Okay, well, the x-intercept -1, 0, we got from this factor here. The power there is 2, so the multiplicity is 2. And since this is the first power of x minus 3, the other one has multiplicity 1. Okay. Now they say to determine the behavior of the graph at those points. So the theory tells us that the behavior here of a 0 or an x-intercept with even multiplicity is that the graph is going to bounce off the x-axis there. So graph bounces. For the other one, it has an odd number for its multiplicity, and it's just 1. And we know from the theory that in such a case, the graph just crosses straight through the x-axis. For factors in the denominator, note the multiplicities of the 0 to determine the local behavior. For those factors not common to the numerator, find the vertical asymptotes by setting those factors equal to 0 and then solving. Okay, so let's get vertical asymptotes. Vertical lines that the curve approaches. Okay, so the way we get that is by, let's see, what number is this? 5. We set the denominator equal to 0 and solve to get vertical asymptotes. Well, again, pretty clear what the solutions are here. We have x equals -3 or x equals 2. And so these will give us, these actually are the equations of 2 lines that the curve will approach, but not cross. The graph of a function can never cross its vertical asymptote. So VA about here at -3. A vertical asymptote about here at 2. So the lines x equals -3 and the line x equals 2, those are vertical asymptotes. Okay. For factors in the denominator common to factors in the numerator, find removable discontinuities. Those are breaks in the graph that can be defined away. They can be removed by just making a slight modification in the definition of the function. But we don't have any of those on this problem because there is no factor common to the numerator and denominator. Compare the degrees of the numerator and the denominator to determine the horizontal or slant asymptote. Okay. Now the degrees here are the same. Okay. Now the degree is the highest power on x. And it's not maybe obvious that the highest power on x is 3. We actually wouldn't know that for sure without multiplying it all out, unless we went on some, other theory. But you could FOIL all that and then multiply by this binomial, and what you would get is x to the third as the leading term in the numerator. X to the third plus a bunch of other stuff. And we know that because, the biggest term is going to be this 1x times another 1x because it's squared, times another 1x. So x times x times x, that's x cubed. Same thing, by the way, we can kind of just look at these constants, 1 and -3, and know that this thing's going to end with -3. But what really matters are the leading terms. Well, something similar is going to happen downstairs. Work, bunch of terms. Well, there's going to be a second degree term and a first degree term and then a constant. And it's clear that the degree of the top is 3 and the degree of the bottom is 3. Degree equals 3. That 3 right there. Same thing downstairs. Degree equals 3. Well, those two numbers are the same. And when the degree of the top is the same as the degree of the bottom, then there is a horizontal asymptote. And that horizontal asymptote is the line y equals, and then it's the ratio of the leading coefficients, right? Well, the leading coefficient is 1. The leading coefficient of this one is 1. 1 over 1 is 1. The horizontal asymptote is the line y equals 1. Horizontal line 1 unit above the x-axis. Okay, so we've done the first 7 things. Then it says sketch the graph. And so basically it just remains to get some more points to figure out, how we're going to hang a graph on all this stuff we know. Okay? Now, to do that, it would be good to have, we definitely would want a point over here on the left. And we would want a point in this interval between -3 and -1. We kind of know what happens in the next interval, but we will need, let's see, actually we know that the graph is going to have to go up like that. We know that because if it were not true, then it would go down like this. But if it did that, we would have another x-intercept, and we know that the only x-intercepts are at -1 and at 3. So we know that much. And then of course we're going to want, actually we know what's going to happen over on the right also, because we have that x-intercept there. So we have, some of this graph that we can just, reason our way to. But then the rest of it, we want a few more points to know how it's going to go. So it's going to have to do something like this over here on the right. Because, it's possible that it would intersect the horizontal asymptote. That is possible. It's not possible to intersect its vertical asymptote, but it is possible that it would intersect its horizontal asymptote. So, we could set this whole thing equal to 1. This whole thing equal to 1 to figure out whether the thing intersects its horizontal asymptote. I don't see that in these steps here. We also know that the graph is going to go that way. Okay. So actually we do know that the graph does intersect its horizontal asymptote right there somewhere in that interval between 0 and 2. Obviously, the graph is going to come down in some way or other and hit -1. Now, -1 is a 0 of multiplicity 2. We learned that the graph is going to bounce there. So actually, we do know that it's going to go like this. Okay, and it's going to come back up. Therefore, the graph will have to approach this vertical asymptote in this way. Now that's ugly looking curve. So let me redraw that. Now, how do we know that it's not going to approach in this way? Actually, because we know that it bounces. We know that it bounces. And we also know that we have all of the x-intercepts. So if it were to go down this way, then we would know that there would be another x-intercept over here, but there isn't. On the left, then, we should have, let's see, it talked about the behavior near the vertical asymptote. So it said for factors in the denominator common to factors in the numerator, find the removal. Oh, yeah, it's not that. 5. For factors in the denominator, note the multiplicities of the zeros. Okay, we didn't actually make a note of that, but the multiplicity of this 0 here is 2, which is even. And that actually informs us about the behavior. Let's see, it says local behavior is what it says. And because that's even, okay, so let me make a note here. Because that is even right there, we're going to have the graph come in the same way. Actually, it's kind of like leaving as we read from left to right, that it's going to come in the next interval. It doesn't approach this vertical line down here, it approaches it up here. And, well, y equals 1 is a horizontal asymptote, so it's going to have to approach that. Okay, so here is a graph of this rational function going through all of these steps. All of those steps represent little problems, which are good problems having to do with rational functions, but put it all together and you can do something pretty amazing, which is to graph a rational function with all of that dramatic behavior it has.